We're going to be looking at graphs of polynomials and applying some different characteristics that we've already looked at, but now we're going to look at more specifically and review with graphs of polynomials. So we're going to come back and we'll label some things on this picture as we talk about those different things. So x-intercepts are the places where the graph crosses or touches the x-axis. So for this graph, we have 3 x-intercepts that we can see on the graph. These can also be referred to as roots, zeros, or solutions if you're working with polynomials and other are asked to do other types of problems. So just know if you see any of those 4 words, x-intercepts, root, zero, solutions, they're all looking for the same thing. We're trying to figure out where the graph is crossed in the x-axis. Our y-intercept is where the graph is going to touch the y-axis or cross the y-axis. That is only going to happen one time when we're looking at polynomials. So the reason that happens is that, again, if it's a y-intercept, that is where x is equal to 0. So if I take this equation or this function rule and replaced all of these x values with 0 and simplified, all of the other terms other than the constant are going to turn into 0, and I'm only left with a constant because I'm adding zeros to it. So one way that you can kind of shortcut this is if you just take your constant for every polynomial, that's going to be your y-intercept. And then what this looks like graphically, of course, is the place that we're touching and crossing. So in most cases, you're only going to have one y-intercept if it's a polynomial function. The next thing that we're going to look at is continuity. So a function is continuous if you can trace the graph without picking your pencil up off of the paper. All graphs of polynomials are smooth continuous lines. So that is just a definition for a polynomial function. If we look more specifically here, this graph to the left is a cubic function. So we're going to talk about in just a little bit how to be able to identify the degree of a polynomial from these kind of smooth continuous lines. But again, I can take that pencil and just keep tracing it, and that shows me that it's continuous, and it would go on to infinity. So we would say it's continuous on all real numbers. This piecewise graph over here, I would have to trace up to the top, and then I'd have to jump back down, and I'd have to skip over some points. So this would be an example of a not continuous function. And so again, on our example up here at the top, we can just recognize that it's a continuous function. You'll get more comfortable with the idea of polynomial graphs and what they look like as we keep talking about that characteristic in this unit in their graphs. The other thing that we need to be able to identify are increasing and decreasing intervals. So a function is increasing if the y values are increasing as the x value is increasing. So what we want to think about for increasing intervals is that we're going to read this graph left to right because the x values are increasing as we move left to right across that graph. Decreasing, again, reading left to right, it's going to look like the function is going downhill. It's really important when you're naming increasing or decreasing intervals that you're using interval notation, so that's parentheses and brackets, and that you're using the x values for those intervals. So a common mistake is to use the y values instead of the x values. So if we go back up here and look at this graph, we can see that if we're reading left to right, we're going to go uphill until we get to a peak up here at the top. So that part would be increasing. And then it's going to turn and we're going to be going downhill or decreasing until we get to this low point, and then the graph turns again and is increasing again. So we have 2 increasing intervals and 1 decreasing interval. And again, we said we're using our x values. So what we're thinking about is, where is this graph breaking apart? So kind of like we did with our piecewise functions, where does that change happen? And so on the x-axis, it's going to be increasing, because again, we're reading left to right. So we're starting at negative infinity until we get to -1. We're using parentheses because actually at that peak, it's neither increasing nor decreasing. So we're not including that value. So then we start decreasing. So if it stopped at -1, it's going to start decreasing at -1. And that happens all the way until we get here to 3 on the x-axis. And then the graph turns again at 3 and keeps increasing to positive infinity. So for increasing and decreasing intervals, you want to make sure that you're talking about the entire x-axis. The other thing that could happen, you could have a constant polynomial function, and so then that would have neither increasing nor decreasing behaviors. But for all the other polynomial functions, we should have increasing and decreasing intervals. The places where the change from increasing to decreasing happens are the local extrema. So extrema is plural for maximum or minimum. And we talk about local maximum or local minimum. So those words are interchangeable. You can see it listed different ways on different pieces of work that you may have, or textbooks that you have in math, but that means the same thing. So extrema is a maximum or minimum. And when we talk about a local max or min, we're thinking about local meaning in the area of. So if you're local to your house or local to your town, you're not traveling far out into the world. You're staying in that particular area. And so that's what we call it, a local max or min on these graphs of polynomials. So if it's a maximum, it looks like a peak on the mountaintop. If it's a minimum, it looks like the valley in between the two mountains. And so we can go back up here. So those points that we found earlier are our local extrema. So if I have 3 intervals of increasing and decreasing, then I have to have at least 2 local max or min. So we would have a local max at that high point of -1, 4. And we would have a local minimum at 3, -4. So again, hopefully all of those vocabulary words and finding those things are a little bit of review. You're fairly familiar with most of those terms. The one new piece of thing that we want to talk about would be the relationship here about the maximum number of local extrema for a polynomial function. So this is a really important thing to think about because this is what's going to help us identify the type of polynomial function that we have from a graph. So the maximum number of local extrema will always be 1 less than the degree of the polynomial. So remember that the degree meant that that was our highest exponent on a term. So if we go back and think about our graph that we had here, at the top, we have 2 local max or min. So we have 1 less, so we would add 1, which means this is a 3rd degree polynomial. It's a cubic function. I just made a hot mess there. There we go. And again, we should be fairly familiar with the cubic function. So this is our non-transform parent function. As we stretch and compress, it makes those hills and valleys a little bit more predominant and easier to see. But if I have 2 local max or min, then we would have a cubic function. And so we can use this property a couple different ways. So again, if I had a graph that looked like this, we would count. We have 1, 2, 3 local max or min, which means this has to be a quartic polynomial because 3 plus 1 is 4. So it has to be a degree of 4. So it would be a quartic polynomial. And it really, like, I could just scribble, and so my heart's content here. That was not a perfectly smooth line there. I can just make this have as many of those bumps as I want. And again, we're counting. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 local max or min, which means this would be an 11th degree polynomial. We're always going to add 1. They could also ask the question, if we had a quintic polynomial, how many local max or min should we expect to see? And we're working backwards, so you do want to be careful because we can get a little confused about where we're adding and subtracting. But if it's a quintic polynomial, that means that we should see 4 local max or min, or extrema. And so if I start to draw that, there's 1, 2, 3, 4. And so that would be the graph of a quintic. So again, it's just understanding the relationship between the degree of the polynomial and the maximum number of the local extrema that we can see. The number is always going to be 1 less than the degree of the polynomial. And then the last question there is about a global maximum. So if we go back to that word local, meaning in the area of, global is the whole graph. So can you find an absolute high point or low point on a polynomial function? Sometimes you can. So if it's a quartic or a quadratic, so something with an even degree, we're going to hit a high point. But if it's something with an odd degree, those ends, if you notice the ends of the graph, we're going to talk about end behavior tomorrow, but the ends of the graph are shooting off in either direction, which means one side's going to negative infinity and one's going to positive infinity, so this one would not have a global maximum or minimum. So some important vocabulary, an important relationship there with the max or min on the graph that you'll need to use throughout the rest of this unit.